Right, morning lads. It's good to see you all on Thursday. Hopefully you had a chance to start having a look at those extra questions that I set. Um, for this lesson, we aren't going to take things that much further, but rather focus in on some different problems that we can solve by applying the same technique. As a warm-up, I've got here a question that's very similar to the one that we looked at on Thursday. And we've got a bung being whirled in a vertical circle at 3 radians per second. And it's the string that the bung's attached to has length 0.7 meters. I'd like you to pause the video and do two things for me. I'd like you to sketch a diagram by copying out this and labeling the forces at 2 points. Point A, the top of the loop, and point B, the bottom of the loop. Once you have done that, I'd like you to go further and using the bung's mass at 50 grams to calculate the maximum and minimum tension in the string. Right, so if we start off with labeling the diagram, let's look at the top point here. There's two forces acting on this bung at each point. We've got the weight at both points, pulling it down, which we can label mg. Sometimes this can be labelled W, either or, doesn't matter, depends a bit on the question. And then we've got to think about the extra force here, which is tension. So in this case, we've got the tension acting in the same direction as the weight. And at this case here at the bottom, we've got the tension acting in the opposite direction. And those are the two forces acting on it. For this next part, we've got, given that the bung has mass 50 grams, calculate the maximum minimum tension in the string. So for this, we've got to use that key formula that I was talking about on Thursday. It really is important that you follow the same process each time with these problems, because otherwise you'll get mixed up and make a mistake with the directions. So it's force in minus force out equals mv squared over r, which equals mr omega squared. Now, looking at this one, it's obvious which one to choose. We've been given the angular velocity, so therefore we should use this version of the formula. The only thing to do is to now separate it into the two different situations, the top and the bottom. These are the points of both extremes in this situation, or any vertical circle for that matter. So at the top, we've got the force in towards the centre of the circle being the tension plus the weight, because they're acting in the same direction, and that equals mr omega squared. We rearrange that for t, so we end up with the tension equals mr omega squared minus mg. And at the bottom of the loop, we're going to do the same thing. Force in, tension in this case. Force out is the weight, T minus mg, equals mr omega squared. Again, rearranging for t, T equals mr omega squared plus mg. Exactly the same way we saw on Thursday. At the top, you're subtracting the weight from this centripetal force term, meaning the tension at the top is always going to be less in this situation than at the bottom, where we're adding the weight to the centripetal force term. So once you've done that, once you're at that stage, you're able to plug your numbers in. Got the radius, remember it's the length of the string in this case, so we have the mass, which we've got to convert to kilograms by dividing by 1,000. So you then plug that into your calculator, you get times by the radius times by square of the angular velocity So after solving that problem for both the tensions, you should have a tension on the top of minus 0.18 newtons and a tension on the bottom of 0.81 newtons. You have a negative tension. What I would like you to do before you move on to the next video is see if you can think about what the significance of that negative tension is, because we know here that that must be a problem.